Factorial ANOVA is similar to one-way ANOVA in many ways. As you'll recall, in one-way ANOVA, we have a single variable called a factor. The factor can take on several values, which in an ANOVA are called levels. In this example, we have 3 levels of distraction: texting on a smartphone, talking on the phone, or no phone, which I'm calling the control group. The numbers in each cell represent the subject's score in the driving simulator. Higher scores mean better performance. If we introduce a second factor, say time of day, then we have a 2x3 factorial design in this example. There are 2 levels of time of day and 3 levels of distraction. Instead of this study, suppose that our researchers are interested in the effects of alcohol use on distraction and driving ability. They set up a driving simulator and ask the subjects to imbibe alcohol before stepping into it. Set up this way, we have a 3x3 factorial study. 3 levels of distraction and 3 levels of alcohol impairment. BAC, by the way, stands for blood alcohol content. In every factorial ANOVA, we're testing 2 kinds of effects: main effects and interaction effects. Let's first take a look at the main effects. Here, I've reproduced the matrix on the last slide, but added a column and a row to hold the averages for each level of each factor. Think of these 2 main effects as 2 separate one-way ANOVAs: an ANOVA for driving skill during the day versus at night, and another ANOVA for driving skill under the 3 different distraction conditions. Just glancing at these data, it looks as if there is no main effect for time of day, since there's such a small difference between the scores for the time of day factor. There is a difference for the type of distraction factor, however, since the means here do show a difference. Let's now look at interaction effects. In this example, I'm not sure that there are any interaction effects. Whether the simulation takes place during daytime or nighttime driving conditions, performance steadily gets better as drivers become less distracted. You can see this more clearly in this graph. The blue line represents performance at night, the orange performance during the day. The square markers represent the scores under the control condition, the triangular ones the scores under the talking condition, and the circular ones the scores under the texting condition. As you can see, the line segments are roughly parallel to one another, which indicates that there's no interaction between the 2 factors. Let's take a look now at another one. This study had to do with frustration tolerance. There were 2 factors: the loudness of a noise and whether that noise occurred under a predictable or unpredictable pattern. Subjects were given a series of unsolvable puzzles, and the number they attempted was recorded over a 15-minute period. That number is the number in each of these cells. As you can see, there was a main effect for predictability, but not for the volume of the noise. In this case, however, there was also an interaction effect. For those in the predictable condition, the volume of the noise didn't make that much of a difference. Both groups attempted about the same number of puzzles. The scores of those in the unpredictable condition, however, varied greatly. Those who experienced a loud and unpredictable noise attempted only half the number of puzzles as those who experienced a soft but unpredictable noise. And you can see this here in the chart. The blue line represents the puzzles solved in the unpredictable condition, the orange in the predictable condition. The round marker shows the outcome for the loud condition, and the square markers for the soft condition. The key thing to look for here is whether the lines are more or less parallel. If they're not, then there's an interaction effect. It's important to remember that factorial ANOVA study can have 1 or 2 or as many main effects as there are factors, and 1 or more interaction effects. Moreover, you can see main effects without an interaction effect, or an interaction effect without any main effects. Let's take another look. Suppose we're interested in testing the effects of sleep and stress on cognitive performance. We'll use mice in our study here and induce stress by injecting them with cortisol. We'll manipulate the amount of sleep they receive by waking them at regular intervals. We'll have a control group that receives the normal amount of sleep, another that's only allowed a moderate amount of sleep, and another group that gets no sleep at all for the 12 hours prior to the experiment. The dependent variable here will be the time it takes for the mice to complete the maze, which they have been previously trained to run. So hopefully it's clear just by looking at this table that this represents a 2x3 factorial ANOVA, since there are two variables, one of which has two levels, no stress and stress, and the other of which has three levels, normal sleep, moderate sleep, and no sleep. Here's the data. As you can see, there's a very small main effect for the stress condition. Let's assume this turns out to not be statistically significant. There's a much larger main effect for sleep. What about interaction? In the no stress condition, it looks like sleep has some effect on the mice's ability in the maze, but the effect is very small and probably not statistically significant. In the high stress condition, though, the effect of sleep is much larger and probably would be statistically significant. Okay, let's talk now about calculating the F ratio for factorial ANOVA. In terms of the main effects, basic concept is the same as it was for one-way ANOVA. The calculations for the interaction effect get very involved, though, so here we're going to have to rely on whatever the software that you're using offers. The most important thing to remember here, though, is that for any factorial design, the number of possible main effects is equal to the number of factors. The number of interaction effects is equal to 1 minus the number of main effects. In this case, there are two factors, sleep and stress, so there are two main effects and one interaction effect. If we added another factor, say the sex of the mouse, we would test for 3 main effects and 2 interaction effects. Okay, let's take a look now at the assumptions for factorial ANOVA. Independence of observations is an assumption we've seen for all the tests that we've run. It means that the measurement of one participant or observation should not influence the measurement of another. Normality of the residuals is similar to the assumption in one-way ANOVA, which states that the data in each condition should be normally distributed. I'm not going to go into this requirement in any detail, discussion about why the residuals need to be distributed normally. It gets much more, well, it gets a bit more complicated. The next assumption we have is homogeneity of variance, which is also something that you've seen before. Just as before, it means that the variances of the independent variables should be about equal for all of the groups. Again, here we'll rely on the Levene test, which SPSS will provide for us to check this assumption. If it's not significant, if the Levene test, in other words, is not significant, then the variances are assumed to be equal. Finally, we'll check for outliers, which can distort the results of any statistical test, and here I would recommend that you use a box plot or something similar, perhaps a histogram. My choice, though, would be for a box plot. All right, let's take a look at what SPSS is going to give us once we ask it to conduct a factorial ANOVA. Let's assume that this data represents the output from a test of two different drugs, drug A and drug B, which treat anxiety and which is being administered at 3 different dosages, a high dose, low dose, and a medium dose. Just like all the other SPS output we've examined, this is just a simple table of descriptives. This is the first thing, by the way, that the SPSS will show you in the output window. I'll reformat this to make it a little bit clearer, but before I do that, let's assume that the higher scores indicate a reduction in anxiety. Okay, so it appears here that there are 2 main effects and possibly an interaction effect. The row and column averages appear to diverge. Those who received drug A showed better anxiety score than those who received drug B. Dosage, though, also had an effect. Both those who received drug A and those who received drug B did better on higher dosages. Now let's look for any possible interactions. For drug A, scores went up a good deal more as dosage increased. Scores also went up for those who got drug B, but not as much. Now the question here is, were these observations statistically significant? First, however, we'll have to check assumptions. We'll assume that the study was designed in such a way that the scores in each group are independent, and we'll also assume that the residuals are normally distributed. We'll use the Levene test to assess the assumptions about equal variances. And as the output shows, the hypothesis that the variances were different was rejected since the significance value here is greater than 0.05. Okay, so now on to the main question about the overall significance of these results. At first glance, it's admittedly difficult to read this table because there's a lot of information, really more than we need here for a factorial ANOVA. There are A rows in the table, but we're only interested really in 3 of these: the row for drug type, the row for dosage, and the row for interaction. It looks like our observation in the table of means are borne out. There's a significant main effect for drug type, and a significant main effect for dosage, and also a significant effect for interaction. Looking at the effect sizes in the last column, you can see that there's a large effect for drug type and dosage, but only a moderate effect for interaction. SPSS will also compute post-hoc tests for factorial ANOVA just the way that it does for one-way ANOVA, but we're not going to cover them here. Okay, well, I hope that helps.